4 billion years ago, asteroids rained down on the newly formed moon, tearing into the surface. Where the fractured crust is thinnest, molten lava seeps from the moon's hot interior, spreads out in giant pools, and solidifies to form the scars we see today from Earth. And strangely, although the moon rotates, the Earth's gravity holds onto it so tightly, the same face points towards us at all times, making the features on the far side of the moon a complete mystery.
For all of history, the far side of the moon was invisible to the Earth. It's the back side. You can't see it.
In 1959, Soviet spacecraft Luna 3 flies past the moon's far side and photographs it for the first time. Astronomers expect to see the familiar dark and light patches. They were in for a big surprise.
When scientists saw the pictures, they were shocked. The far side looked completely different than the near side. It's saturated with craters. It just was such a huge dichotomy. Nobody was expecting that at all.
The far side still had massive impact craters, but it was uniformly pale. It seemed like no dark lava had bled out onto the surface at all. But why?
The only solution we could come up with is there's a difference in thickness between the crust of the near side and the crust of the far side. The backside must be so thick that lavas are not able to come up through them and erupt out onto the surface. Instead, on the front side, where it's very thin, lavas can easily come up through cracks and flow out onto the surface.
Recent NASA missions confirm the crust on the back of the moon is around 30 miles thicker than the crust on the front.
The far side is thicker. It's not like, oh, part of it is and part of it isn't. No, it really, the other side of the moon has a thicker crust than the near side. That's bizarre.
So one of the biggest mysteries in planetary science over the last about 50 years is, why is the crust of the far side so thick?
The impact theory doesn't really cover that. It just forms the moon, but it doesn't say why one side should be so different than the other one, unless something strange happened.
The new age of supercomputers brings about the first credible explanation. The impact of Theia could have made two moons, not one. And this double birth might also explain our double-sided moon. According to the theory, 4.5 billion years ago, there are two moons in the night sky. The smaller moon chases its larger sibling, gradually getting closer. Eventually, the two moons mush together in slow motion, and the smaller moon covers the far side of the larger moon, creating a new, much thicker crust.
Not all impacts are high-speed, super violent events that eject material everywhere. Instead of just wham, smacking into it, it would have just merged with it, just been pulled apart and smeared out over the moon.
Essentially, when you look at one half of the moon, you see more of one body, and when you look at the other side of the moon, you see more of the other body that kind of wrapped around the first body, and so it's thicker on that side.
It's the brightest and most noticeable object in the night sky, but if you spend much time observing it, you will see that the moon is never quite the same from one night to the next. The moon has something we call phases, which means that it appears to change shape a little bit every night. To understand why this happens, we need to talk a little bit about the way the Earth and the moon move together in space. The moon orbits around the Earth, much like the Earth orbits around the sun. However, while the Earth takes about 365 days to travel once around the sun, 1 year, The moon completes its orbit around the Earth in only 29.5 days, or about 1 month. That's actually where the idea of months came from, the time it takes for the moon to complete one orbit around the Earth. And the words moon and month come from the same root. Despite how bright it looks in the sky, the moon does not have any light of its own. It only appears to shine brightly in the sky because light from the sun hits it and bounces off. Just like the Earth, the moon has a day side and a night side, with half of it in sunlight and half of it in darkness at any one time. As the moon travels through its orbit around the Earth, that dividing line between day and night, called the terminator, is visible from different angles, giving the impression that different amounts of the moon are lit up on different days. The cycle of lunar phases begins with the new moon. At new moon, the moon appears completely dark because the unlit side is facing the Earth. New moon is the only time in the lunar cycle when a solar eclipse could happen, because it is the only time that the moon is between the sun and the Earth. After a few days, once the moon has moved along a little in its orbit, we can begin to see some of the moon's day side from Earth. What we see is just a thin slice of light called a crescent. We call it a waxing crescent because waxing means growing. The crescent moon will grow a little bit thicker every night until it reaches the next phase, first quarter. The first quarter moon is sometimes called the half moon because it appears to us that half of the moon is illuminated, but it is called first quarter because the moon is 1/4 of the way through its cycle. As the days pass, the moon continues to grow, soon entering its next phase, the waxing gibbous. Gibbous means humped or swollen, and again, we call it waxing because it grows thicker every night until it reaches the next phase, the full moon. A full moon is the biggest, brightest, and easiest phase of the moon to see. The moon rises at sunset and is up all night, so if you are outside and the sky is clear, it's hard to miss. The moon is halfway through its orbit around the Earth and is now on the opposite side of the Earth from the sun. During a full moon is the only time that a lunar eclipse can happen, because that is the only time that the Earth's shadow could fall on the moon. As the moon continues in its path, it appears to shrink again as we begin to see more and more of its dark side. A few days after the full moon, the moon will be a gibbous again, but this time it's a waning gibbous. Waning means shrinking or getting smaller, and so the moon will be waning for the rest of its orbit. The next phase is another half moon, but this time it's called third quarter, or sometimes last or final quarter, because the moon is 3/4 of the way through its orbit. Soon the half moon shrinks into a waning crescent, which will continue to shrink night after night until it vanishes completely into the next new moon. Big and bright and beautiful, different every night, but repeating the same cycle over and over, the moon is one of the best objects in the sky to observe, especially for someone just getting started. The next time you look up and see the moon in the sky, take a moment and see if you can identify which phase of the moon you're seeing, and try to figure out which one will come next.
In this video, we're going to take a closer look at an astronomical event called a lunar eclipse. To begin our investigation, it's important to understand the natural phases of the moon as it revolves around the Earth. These moon phases occur over the course of a month and are due to the moon's relative location to the sun with respect to the Earth. This monthly cycle is important, as a lunar eclipse can only occur during a full moon, when it is opposite the Earth from the sun and fully illuminated. On rare occasions, the full moon lines up precisely on the ecliptic plane, the plane on which the Earth rotates around the sun. When this happens, the Earth blocks some or all of the sun's light and casts a shadow on the moon, which we see as a lunar eclipse. During a lunar eclipse, the Earth's shadow has two distinct parts. The umbra is the inner cone-shaped part of the shadow, is the part in which all the light has been blocked. The penumbra is the outer part of Earth's shadow, where sunlight is only partially blocked. Scientists recognize three types of lunar eclipses: penumbral, partial, and total. A penumbral eclipse occurs when only the penumbral shadow is hitting the moon. A penumbral eclipse is very hard to see because of all the parts of the moon are still receiving some light from the sun. A partial lunar eclipse happens when a portion of the moon enters Earth's umbra, while the rest of the moon remains in the faint light of the penumbra. In a total lunar eclipse, the moon is entirely in the Earth's umbra, casting a shadow across its full visible surface. But even in a total eclipse, the moon remains faintly illuminated by indirect sunlight refracted through the Earth's atmosphere, giving the moon a faint red glow. Partial lunar eclipses occur at least twice a year, but total lunar eclipses are less common. If you're lucky enough to see one, be sure to get out your camera, as a lunar eclipse provides an opportunity for some amazing photographs.
For thousands of how-to and advice videos on any topic, visit monkeysea.com.
Hi, I'm Emerald Robinson. In this What Is video, we're going to take a closer look at solar eclipses. A solar eclipse occurs when the new moon passes between the Earth and the sun. For a few brief moments, the moon's shadow blocks sunlight from reaching the Earth. A total solar eclipse completely blocks our view of the sun, while a partial solar eclipse only covers part of the sun. Solar eclipses are rare events and only last for a few minutes, as the moon's shadow is small in comparison to the sun. Astronomers can predict when eclipses will occur based on the Earth and moon's positions relative to the sun. Solar eclipses only occur during new moons when the moon's surface is in shadow. During an eclipse, the temperature may drop due to the loss of sunlight. Stars may appear in the sky and birds may start singing, tricked into thinking it's either dawn or evening. Solar eclipses were met with fear in ancient times and are still viewed as unlucky in some parts of the world. Astronomers view solar eclipses with excitement. During a total solar eclipse, the sun's corona is visible surrounding the moon's shadow. The corona is the outer atmosphere of the sun. Much cooler than the sun, the corona is not normally visible to the eye. During an eclipse, it's also possible to see solar prominences, streams of solar material ejected from the sun's surface. Looking directly at the sun may result in permanent eye damage and even blindness. A total solar eclipse only covers the entire sun for a few moments, and even during this time, directly viewing the eclipse with the naked eye risks eye damage. Astronomers advise not taking the risk. View the entire eclipse through special eye protection and filters, and then you can truly enjoy one of the sky's most spectacular displays.
For thousands of how-to and advice videos on any topic, visit monkeysea.com.
In 1959, the Soviet spacecraft Luna 3 beamed back images of something Earthlings had never before seen: the far side of the moon. We always see the same old side of the moon because the moon rotates exactly once on its axis each time it orbits Earth. If it weren't spinning at all, we'd get at least one 360-degree view of its surface with each lap. If it were spinning twice as fast, we'd also see the moon's entire surface more than once per orbit. But instead, our moon's motions, like the spin and orbit of most other moons in our solar system, are remarkably in perfect sync. This wasn't always the case. Our best guess is that our own moon formed due to a massive asteroid impact, and its initial spin and dizzying 10-hour orbit were almost certainly not in sync with each other, though we don't know which was faster. At such close range, Earth's gravity deformed the moon into a slight oval, with one of its bulges facing Earth. Those bulges quickly swung out of alignment thanks to the moon's asynchronous spin and orbit, but Earth's gravity continually squeezed them back again. What's more, this gravitational tugging would have influenced the moon's rotation rate. If it was spinning more than once per orbit, Earth would pull at a slight angle against the moon's direction of rotation, slowing its spin. If the moon was spinning less than once per orbit, Earth would have pulled the other way, speeding its rotation. Whatever the case, it took just 1,000 years for the Earth's pull to adjust the moon's spin enough that one rotation of the moon corresponded to one trip around the Earth, leaving one side forever locked facing away. We do end up seeing some of that far side because the moon's elliptical orbit gives us peaks beyond its average eastern and western horizons, and its tilted axis causes moon seasons, revealing more of the lunar north or south poles. But those glimpses only add up to an extra 9%, leaving 41% of the moon hidden from Earth. Satellites, starting with Luna 3, have allowed us to map the rest, but it's safe to say that our relationship with the moon is still pretty one-sided. I'd like to say a big thanks to Squarespace for supporting this episode of Minute Earth. Squarespace is an incredibly easy way for you to create a beautiful website, blog, or online store. It has an elegant interface, beautiful templates, and 24/7 customer support. You can try Squarespace out with no credit card required by heading to squarespace.com/minuteearth to get 10% off and start building your website today. Again, we thank Squarespace for their support of Minute Earth.